Oh, great, you can hear me. All right, let's go ahead and get started. So, good afternoon, everyone. Thanks for being here. My name's Christopher Domas. I wanted to talk to you a little bit about a project I've been working on recently that I call the movfuscator. But before we get into any technical details, I wanted to give you a little bit of background information on this project. So this whole thing started when I was bored one weekend and I was browsing a site called REmath. So if you haven't been to this GitHub place, it's absolutely fascinating, just tons and tons of awesome articles. I love reading things here. So check that out as soon as you can if you haven't seen it already. So I was browsing through some things on REmath, looking for something interesting. And I found something that caught my eye, an article by a guy named Stephen Dolan. So Dolan's article started out with this humorous observation about the x86 architecture. Dolan says it is well known that the x86 instruction set is baroque, overcomplicated, and redundantly redundant. We show just how much fluff it has by demonstrating that it remains Turing complete when reduced to just one instruction. So that really caught my attention right away. I thought, I've been using x86 for a decade, and I didn't know one of these instructions in this architecture was Turing complete by itself. What instruction is this, Dolan? What magical, powerful instruction is so awesome that it is Turing complete on its own? And it turns out it's the move instruction. The simplest instruction in the entire architecture, moving data from one place to another, is apparently Turing complete. So what does that mean if move is Turing complete? Well, sort of at a high level, it means that any code that we write could be written as a set of moves instead, and absolutely nothing else, just a bunch of moves. And that just boggled my mind at first. I thought, really? I mean, when you think of all the incredibly complicated things we do with our code, like arithmetic and comparisons and jumps and function calls and exception handling, to then tell me that move can do all of these things on its own, that seems impossible. But if move is Turing complete, then that's the way it is. So the more I thought about that, the cooler it seemed. Suddenly I kind of realized that'd be pretty hard to reverse engineer, wouldn't it? Because we'd go from something like this, where we've got all these nice instructions that tell us exactly what this code is doing. In just a matter of seconds, I can look at this and see that we're initializing a variable to 0. Then we're pushing a string onto the stack and printing it out. We're removing an argument from the stack. We're incrementing our local variable by 1 and comparing it to 100. And if it's not 100 yet, we're repeating 100 times this whole thing in a loop. So just by looking at the mnemonics in this, in a couple of seconds, I can reverse engineer it and understand exactly what this code is doing. But if move was Turing complete, if we rewrote this whole thing as a series of moves, we'd go from this, where we've got all these nice clues, into this, just a whole bunch of incomprehensible data transfers from one location to another. We would lose all the clues that we use for reverse engineering software, and that seemed like it would be devastating for reverse engineering efforts. So I thought that was really cool, and I wanted to pursue it more, but in order to use this idea, we need to understand a little bit more about what a Turing machine is. So if you're not familiar with this concept, a Turing machine sort of at a high academic level is really just this 5-tuple where you've got this finite set of states Q, a distinguished starting state in Q, a finite set of symbols sigma, and one of those is a blank sigma. And then you've got this transition table delta that maps the cross product of Q and sigma to the cross products of Q, sigma on either left or right. And what that really gives you is a state transition diagram, a way of moving from one state to another. And that's exactly how Dolan approached this problem in his article. He designed his own little Turing machine and showed how you could move from one state to another using only the move instruction. And through his abstract Turing machine, by showing that it could work with just move, he proved that move is Turing complete. So that's really, really cool, but that's really purely academic, because as soon as you try to actually apply this concept, what you're going to find is that this idea of this abstract state transition diagram just doesn't really map well to the processors that we use every day, meaning that the ideas from this article, although they're really fascinating, just aren't that useful in practice. And Dolan acknowledges this. He sort of concludes his article with a tongue-in-cheek observation. He says, removing all but the move instruction from future iterations of the x86 architecture would have many advantages. The instruction format would be greatly simplified, the expensive decode unit would become much cheaper, and silicon currently used for complex functional units could be repurposed as even more cache, as long as someone else implements the compiler. So I was absolutely fascinated by his article and really amused with his approach. So I read that last piece and I thought, you know what, I'll take you on, Dolan. I can implement the compiler for you. Challenge accepted. So I set out to implement Dolan's move-only compiler, but it was a little bit daunting to start on this thing. because like I said, his ideas are so far removed from any practical application that they're a little bit hard to use. But there were a few key ideas from his article that we can pretty quickly adapt. His first key idea was that move can check for equality. We don't need a comparison instruction because move can do it for us, and it's just this simple. For example, if we have two variables, x and y, and we want to see if these variables are equal to each other, all we have to do is move 0 into the memory pointed to by x, move 1 into the memory pointed to by y, and then read back from the memory pointed to by x. So imagine x and y are both 3. Both of these are equal to each other. Then this is move 0 into memory address 3, move 1 into memory address 3, overwriting the 0, and then read back from memory address 3. Well, the last thing we wrote to memory address 3 was a 1. R becomes 1, indicating that these two things are equal to each other. But now suppose they're not equal. Suppose x was 2 and y was 3. This is move 0 into memory address 2, move 1 into memory address 3, and read back from memory address 2. Well, the last thing we wrote to 2 was 0, so R becomes 0, indicating that these things are not equal to each other. So with just 3 move instructions, we can actually check values for equality. Another key idea from Dolan's paper is that there's really only one code path. If all you've got is a bunch of moves and no branches, everything executes all the time. But Dolan observed that if you design this thing correctly, a block of move instructions can actually either have an effect on the system state or have no effect on the system state, all depending on the initial state of the system. So we'll show a little bit more of how we can use that later on. Dolan's Turing machine required a single jump instruction to loop back to the beginning of his program. That sounds kind of like it's cheating. If we're trying to prove that move is Turing complete, we can't just start tossing in jump instructions. But I'll show later that this is kind of incidental. We can actually get away from this jump instruction, but it's a useful starting point for our design. But what that would look like is we're going to have a whole bunch of move instructions in a row, followed by, at the very end, a jump back to the beginning. So somehow this whole thing's going to execute over and over and over again in a loop, and it's going to magically do computation for us if we can make this work. Another key idea from his paper, his Turing machine required an invalid memory address for halting. If you imagine we've just got these moves executing in a loop forever, we need some way to stop the program. So Dolan said, assume my Turing machine has some invalid address, and when I try to access that address, the program stops. So that was another useful idea that we can adapt. So we've got these basic ideas of how to use move for some useful stuff, but it's a little bit challenging to get started with this. But I thought maybe if we can build on these primitive Turing machine operations that Dolan came up with, we could maybe adapt those for some higher level logic. We could also change his Turing machine. His thing just works on abstract symbols. If we want to actually apply this, we need something that will work on real data. So we'll adapt this for real data, and we'll start adding new operations. We can gradually build up operations for if, else, arithmetic, logic, jumps, loops, everything else our program needs to do. We can add these piece by piece using move instructions. And maybe if we do all those things, we can actually get this a little closer to something we could use in practice. So let's look at how we would actually build up some of these operations. Let's look at one of the most critical ones for programming, if. How do we build an if statement using only move instructions? So we want to design something like this. If x and y are equal to each other, then assign 100 to the value x. So pretty simple at this level, but we've got a big catch if we want to just use move instructions. Namely, we have no branches. Going back a slide, if we don't have any branches, I don't have any way to skip this x equals 100 if x and y are not equal. All the paths are going to execute all the time, no matter what. So the solution I came up with for this is that we can sort of force a path to operate on dummy data if we don't want its results, and real data if we do want its results. So that would look something like this. We're going to have a real copy of our data. This is our real system state sitting in this copy of the data. And we're going to have a scratched copy of our data. This is our fake system state that just gets discarded and never really used for anything important. Then we're going to have a selector, basically a pointer, that will let us select between the real system state and the fake system state. And what we'll do is we'll evaluate the first part of this if statement. We'll see if x and y are equal to each other. If they are, then we're going to load our selector with a pointer to the real data, so that when we execute x equals 100, that 100 is going to get stored into the real copy of the system state. On the other hand, if x and y are not equal to each other, we're going to load up our selector with a pointer to the fake data, to the scratch system state. Our x equals 100 is still going to execute, but now that 100 is going to be stored to the scratch state instead of the real state, effectively discarding the results. So that's how we can sort of implement if statements using just move instructions. And see, that's going to look a little bit something like this. We've got an array of 2 pointers. One pointer points to our dummy data, one pointer points to the real data. Then we use our equality check to select either between the real pointer or the fake pointer. We dereference that pointer and we assign 100 to whatever it points to. So without any actual branches, we've just effectively implemented this if statement using this pointer selection method. So in assembly, that would look something a little bit more like this. We're going to have a real copy of both of our variables and a fake copy of both of our variables. And then we're going to have these selection arrays that let us choose between the real copy and the fake copy. And the move instructions themselves to implement that if statement are going to look like this. At first, we're just going to do the equality check that we already talked about to determine if x and y are equal to each other. If so, EAX gets set to one thing. If not, it gets set to something else. Then we use EAX as an index into our pointer selection table to select a pointer either to the real data or to the fake data. Then we dereference that pointer and store 100 to whatever it points to, effectively storing 100 to x if x and y were equal and storing it to some scratch data if they weren't. So really we can implement any if statement then just by adding these selector functions, which are really just pointer arrays, to all of our variables to let us switch back and forth between real and fake data. Now, if you're paying close attention, you might have noticed that there's a little bit of a problem with this equality check I showed. We're sort of reading this variable x and then trying to assign 0 into whatever memory address that is. You can't really write to any arbitrary memory address. That's a good way to seg fault. So we can get around this if we limit ourselves to byte-sized data and just create a scratch 256 element array for this equality check. So I'm going to skip the details of that for brevity, but if you're really curious as to how we get around the seg fault issue with these equality checks, you can check out those slides later. So we've got a way to do if statements. We're getting there. With a few simple extensions, it's not too hard to imagine how to do if-else statements or if-else statements or inequality checks. Those are all pretty easy extensions to our basic if statement thing. If we have to write all of this in just moves, this is going to get really, really tedious in a hurry. So we built up some simple assembly macros using NASM syntax macros so that we can have some high-level functionality that's going to expand to move. So this is a macro for checking two values for equality using only move instructions. This is for checking two values for inequality. And this is a macro for setting up those selector arrays to check or select between real and fake data. So we're getting further. But what we really want, beyond just ifs, is a way to do loops and branches. But we can extend that if-else idea in order to make this work. So here's how we can do arbitrary branches with only move instructions. Essentially, every time we have a conditional jump that we want to perform, we're going to check, should that branch be taken? If it should, then store the address that we're trying to branch to. We can do that with a move instruction. And then turn execution off. And when I say turn execution off, I mean simply switch all your pointers over to dummy data so that anything that executes will not have an effect on the real system state. On the other hand, if the branch is not taken, simply leave execution on and work on real data. Then on each basic operation, not every move instruction, but each primitive operation you're trying to perform, you're going to check, is execution on? If execution's on, just run the operation on real data. If execution's off, you need to check, should I turn execution on? In other words, is the current address the stored branch target? If it is, turn execution on and run the operation on real data. If it's not, turn execution off and run it on the dummy data. So that's really, really complicated and a lot to take in at first, but it's pretty simple with an illustration. So this is what our program looks like. A whole bunch of moves followed by a jump back to the beginning. And these are just going to execute in a loop. And let's say I wanted to branch from this location in my program to this location in my program using only move instructions. It's actually not too bad. At this location in the program, we're going to store the target that we're trying to branch to. I'm trying to branch to address 100C. So we're going to store that somewhere at this location in the program. Now I'm going to turn execution off. And by turning it off, I mean we're going to switch all our pointers over to dummy data so that any memory writes that occur don't affect the real system state. So I turn execution off by switching all those pointers over. And then I allow execution to continue. So all these moves happen, but they're all going to be affecting dummy data instead of real data. Each of these basic blocks is going to check if it's the branch target or not. If they're not the branch target, they just operate on the dummy data having no real effect. So we just continue execution, each block checking if it's the branch target until finally we hit 100C. 100C sees that it's the branch target, so it switches execution on. In other words, it switches all the pointers over to real data instead of fake data, so that now any of the subsequent moves will actually have an effect on the system state. So this effectively implements branching just by switching execution on and off whenever you want to take a branch. So we're getting a little bit further, but we've still got a long ways to go. If we want to do anything useful, we've got to be able to do computation. We need to be able to do arithmetic. Arithmetic actually turns out to be surprisingly easy with move instructions, especially given that we've already constrained ourselves to 1 byte values. So we can actually do basic arithmetic with simple lookup tables, which will allow us to use move instructions for this. So that would look something like this. Let's say we wanted to implement the increment function with move instructions only. Well, we can make a lookup table for that. So what this will allow us to do is if we want to figure out what is 3 incremented by 1, I go to element 3 in my lookup table. So this is 0, 1, 2, 3. So I find that element 3, or 3 incremented by 1, is simply the value 4. So in assembly, that looks something like this to build up our table, and something like this as our actual increment instruction. So really, really simple. One move instruction performs increment. It simply goes to the table, looks up an element in the table, reads it out in order to increment that value. So increment couldn't be easier with move instructions. Same with decrement. We can build up a decrement table. So if I want to figure out what is 2 minus 1, I go to element 2 in my table. This is 0, 1, 2, and I find out 2 decremented is 1. So same basic thing. We can build up a decrement table with assembly macros, and that's our decrement instruction as a move instead of a dec. So we're getting a little bit closer. We've got some really, really basic arithmetic now. We still need logic gates. We need to be able to say things like and, or, not, stuff like that. And we can do that with lookup tables too. So this is a little bit easier to visualize in C. Let's say we wanted to figure out what is the logical and of 1 and 0 without using an and instruction, just using lookup tables. Well, we can do that with this table. I go to array 1 in the table, element 0, to figure out the logical and of 1 and 0 is 0. What about the logical or of 0 or 1? I go to array 0 in my or lookup table, element 1, to figure out the logical or of those two values is 1. So we can pretty easily build up these tables. These are the logical or tables as assembly macros, logical and tables as assembly macros, logical not, all expanding to simple move instructions. We need a way to stop our program if we're just executing these loops or executing these moves in a continuous loop. We've got to have some way to stop this whole thing. Right now, our program loops forever. Fortunately, Dolan figured this out for us. He said, assume we've got some invalid memory address, and when we access it, the program stops. So that should sound kind of familiar. That's basically just null. When we access null, our program stops. It's seg fault. It's not the cleanest way to stop, but it stops. So we'll use null as a convenient way to just stop our program execution. So all we really got to do is try to access the null pointer in order to halt execution. Obviously, we don't want to access null and halt our program every single time. We want to be able to conditionally do that. So we can do that with lookup tables as well. This is a way to conditionally look up either a real pointer to real data or the null pointer to 0 and dereference that to conditionally halt the system. So we're really getting there. We've got all these building blocks now as assembly macros that expand to move instructions. So we've actually got some high-level logic going on here. We've got macros for equality, inequality, not, and, or. We have ways to get real and fake data, ways to increment, decrement, and turn execution on and off. We've built all the macros we need for some high-level logic at this point. And if you build up enough of these macros, programming this way actually becomes almost doable in assembly. But if we want to be really useful, I'd like to be able to go beyond programming with assembly macros. So C compiler is a lofty goal here. So I want to start with something similar. So I promised a compiler for this talk, but I didn't actually say what we'd be compiling. So we're going to start off with a really, really simple programming language, which some people call something else. I'm going to call this Brain Yucky for the purpose of this talk. So Brain Yucky is a minimalistic, esoteric programming language. It's really simple. It's got 8 basic instructions and only 2 registers, an instruction pointer and a data pointer. So these are the 8 Brain Yucky instructions we're interested in. In Brain Yucky, you can increment or decrement your data pointer. You can increment or decrement the byte pointed to by the data pointer. You can read a byte in. You can print a byte out. You can branch forward, and you can branch backwards. So 8 really simple instructions. I'm adding one more to allow our programs to halt. So just a little bit of introduction to Brain Yucky if you haven't seen it before. This is what printing out 1, 2, 3, 4 would look like in Brain Yucky. All of your memory starts with zeros in Brain Yucky, and we want to print out 1, 2, 3, 4. ASCII 1 is hex 31, so we need to get one of our zeros up to the value 31 in order to print this out. So I increment our current data cell, the cell pointed to by the data pointer, 31 times in order to get it up to ASCII 1, and then I print out that 1. I increment it again to get it up to 32, print out the 2, et cetera, to print out 1, 2, 3, 4. Another common paradigm in Brain Yucky is this little chunk here. This is how we set data cells to 0 in Brain Yucky. What this says is check the current data cell. If it's 0, then branch over here. If it's not 0, then decrement it. check it again. If it's 0 now, continue. If it's not 0, branch back. So all this does is it sits in a loop, decrementing the data cell one by one until it reaches 0. So that's how we set a value to 0 in Brain Yucky code. So you can actually build up some real programs with this. Brain Yucky's Turing complete, meaning we can write anything in Brain Yucky that we would in any other language. So this is Hello World in Brain Yucky. They do some complicated loops to get their data cells right up around the ASCII values that they're going to need. Then they start printing things out. So this prints out the capital H, shifts over a data cell, decrements it down to a lowercase e, prints out the e. Then it starts incrementing the e, F, G, H, I, J, K, L, prints out 2 L's. Increments it, N, O, L, M, N, O, prints out the O, et cetera, to print out the whole Hello World program. We can get more complicated. This is a Fibonacci number generator in Brain Yucky. This is 99 bottles of beer on the wall in Brain Yucky. You can really program anything in this. The thing is, this is even worse than the moves ever were. So why on earth would we try to add this to our design if it's this ridiculous? Well, with the building blocks that we've already built up, the things we've already talked about, it turns out it's actually really, really easy to implement these Brain Yucky operations with just the move instruction, which means that if I can get the code that I want into Brain Yucky, then I can easily convert it into only move operations. And going into this, I actually knew that there existed a pretty decent basic to Brain Yucky compiler already. So by chaining together these compilers, I could actually go from from basic into only move instructions. So let's look at how a Brain Yucky to move compiler would actually work. It's going to start out by simply using some moves to read in the current Brain Yucky instruction. Then we're going to figure out what that instruction is using our equality macro. Again, this equality macro expanding to a bunch of moves. We're going to see, is the instruction output? Is it input? Is it incrementing or decrementing the data pointer, et cetera, et cetera. So we're going to figure out what that Brain Yucky instruction is. So this is what the increment Brain Yucky instruction would look like as a set of moves. First, we're going to check if execution is on or not. If execution is on and we're dealing with the increment instruction, then select the real data pointer. If neither of those, or if either of those things are false, go over to the scratch data for execution. Read in a value from the data cell into AL, and then use our increment table to figure out what AL incremented by 1 is, and then store it back into either the real data if these conditions were true or the fake data if these conditions were false. So that's sort of what all our instructions are going to look like. Check if this is the right instruction, load up your selector with either a real or a fake data pointer, and then carry out the instruction. Decrement's pretty much the same. Increment and decrement the data pointer are really pretty basic. Halting the system is pretty easy. We already sort of saw how to do that by dereferencing the null data pointer. Input and output get a little bit more complicated in Brain Yucky. So we start out sort of the same way we always did. Check if this is the right instruction, set up the system state accordingly. But you'll notice down here I've got something that's not a move instruction. At the end of the day, I need to ask the operating system to do this I/O for me, to actually output something to the console or read a value in from the console. So that kind of felt like cheating, but it was an easy way to get started. I'll actually show how we can fix that later on. But for now, we're using the int80 instruction to do this. Comma is reading data in. These are the move instructions for reading data in. Branching gets a little bit more complicated, but it's still not all that bad. So all we're doing is checking, are we on the branch instruction, and is execution on, and do we want to branch? If all those things are true, then we turn execution off. We switch over to those fake data pointers and continue execution. Branching backwards, pretty much the same thing. So we've got all these Brain Yucky instructions, and we've now got ways to translate those into only move instructions. And collectively, that's what I called the movfuscator, a way to translate Brain Yucky into only move instructions. So let's look at a really basic example of using movfuscation. So I've got this Brain Yucky program. This is a ROT13 cipher written in Brain Yucky. What the movfuscator lets us do is it lets us take that code and compile it into only move instructions. So I just gave the compiler, the movfuscator, our ROT13 Brain Yucky cipher, and I had it output a set of assembly for that cipher. So then we're going to use NASM to link this thing. And we're going to use, NASM to assemble this thing, and we'll use LD to link this thing. So finally, I've got a ROT13 program written in only move instructions, or mostly move instructions. So let's see what this looks like. So there are move instructions for our ROT13 cipher. You can tell it, it got a little bigger than it might have been by other techniques. So it's mostly move instructions. We've got that jump at the end that I talked about. We've got those int 80s that I talked about. So I'll fix those in a little bit. But we can see now it can actually do computation for us, which is kind of cool. It's just a whole lot of move instructions executing in a continuous loop doing computation. I think that's actually kind of awesome that this actually works. But there's something that really, really bothered me about this. Even though that int 80 instruction and that jump instruction at the end don't really violate the Turing completeness of this, and I don't think they violate the spirit of the project, it really bothered me that I had two non-move instructions in this loop or in this program. So I racked my brain for a while trying to come up with how to fix that problem so that we could really only have move instructions. And eventually I came up with a way to do it. It wasn't too hard to get rid of that int 80 instruction. So before our program starts to execute in our environment setup, we can sort of get rid of this int 80 with MMIO. So sort of in our start function before our real program begins, we'll just set up the environment to call mmap to map standard in and standard out into the process's memory space, allowing us to access the I/O streams through move instructions. So we can get rid of int 80 that way. That was pretty easy. That jump at the end, that was a little bit more problematic. We need to somehow perform a jump using only move instructions. And in a lot of architectures, you can load the instruction pointer directly with a move instruction. You can't do that in x86, so we've got to get a little bit more creative. So the way I came up with for this was to set my series of moves to be their own exception handler. And then at the very end of the series of moves, we're going to trigger a very specific exception. So we're already using the segfault exception to halt the program. I need to find a different exception, so I decided to use the illegal instruction exception handler to do this. So in our start function, before our program really begins executing, we'll call the sig action function in order to set up our program as its own exception handler. We need to set this no defer flag, allowing our exception handler to recursively trigger exceptions. So we'll call that as well to set that up. Finally, the key piece to all of this is replacing that jump instruction with an illegal move. And when I say illegal move, I don't mean just a move that's going to fault. I don't mean something like accessing the null pointer. That's actually a memory access violation rather than an illegal move instruction. As far as I could think, I could only think of one illegal move instruction in all of x86, which is trying to load the code segment register with the move instruction. They want you to load the code segment registers other ways. If you try to do this, this instruction does encode, but it's their only invalid move instruction. So replacing that jump with this invalid move instruction will cause this exception to trigger, causing the program to jump back, lost my mic, to the beginning to handle its own exception. Finally, since we're going to be calling this exception handler recursively, we need this to not overflow the stack, so we'll reload the stack pointer every time this loop executes. So that pretty much gets us to our new version of the movfuscator, where we can use only move instructions, but we've got a big problem if we have to write all of our code in Brain Yucky, because that's way worse than just dealing with the assembler. So that's where this other compiler comes into play. This basic to Brain Yucky compiler allows us to write our code in BASIC and then feed that into the movfuscator to come up with move-only code. So let's look at a demo of how that kind of thing might work. So what I've got here, if I can find it, so I wrote this little basic program here, 99 bottles of beer on the wall. Not a whole lot to it, just written in BASIC. We initialize a variable to 99. We start a loop. We call our first set of lyrics, call our second set of lyrics, call the first set again, print out, take one down, pass it around, decrement our bottles of beer, repeat the lyrics, and continue until we reach no more bottles of beer. Not a whole lot to that. Lyrics 1 checks how many bottles of beer we have left. It prints one thing if we have none. It prints something else if we have some. Lyric 2, same thing, prints one thing if there are bottles of beer left, prints something else if there aren't. And finally, there's this little done chunk at the end, which we might get to if there's time today. But what we can do is we can use this BF Basic compiler to take our basic code and translate it into Brain Yucky code. So now when I open up our newly created Brain Yucky file, you can see our compiler just created this 15,000 instruction Brain Yucky program to implement 99 bottles of beer on the wall. So all we've got to do at this point is give that to our movfuscator in order to build a move-only version of this program. So the movfuscator just took that brain yucky code, outputted assembly. We used NASM to assemble that, and LD to link the whole thing together. So now if we look at this, we've got our move-only code. It really is only move instructions for the entire program. We got rid of those pesky int 80s. We got rid of that jump at the end. I think this will finish dumping sometime before the end of my presentation, but it's a sizable amount of move instructions. Let me see if we'll give it a few more seconds. All right, so you can see So you can see now at the end there, we got rid of that jump instruction. It's just an illegal move instruction now. That's going to trigger an exception, causing this whole thing to re-execute forever in a loop. So we can go ahead and run this thing. And when we do that, nothing will happen at first, because it's really, really, really slow. But it does work. It just takes a little while. Let's give it a second. We can find out how many bottles of beer are left after we take one down. 98. So it seems impractically slow. This seems totally unusable, and it probably is totally unusable, but I think it's really, really cool because it's not just a giant printf, right? It's not just printing all the lyrics at once. It's actually doing arithmetic and comparison and branches and function calls all with only the move instruction. That's really, really neat that move can do everything for us. And I wanted to really highlight that fact that we can do really advanced things with only the move instruction. So here's a factorization program using only the move instruction. You know, factorization's not an easy thing. It's factoring large numbers using only data transfers. And of course, it seg faults at the end to stop the program. We can find prime numbers using only move instruction. So again, doing really complicated math and arithmetic just by moving data from one place to another. In fact, here's a complete CSS decryption cipher written with only move instructions. I don't know why you would want that, but you could get that. What else? So here's a complete role-playing game that I compiled into only move instructions. I even movfuscated my movfuscator. So I've got a program written in only move instructions that will compile other programs into only move instructions. And that one's never going to finish dumping, so we're just going to kill that as well. So the point is, this is kind of neat. We can do anything with move instructions. So now that I had sort of gotten the concept proven out and knew that I could do this, I wanted to readdress my original question of is this a real anti-reverse engineering technique? How would an experienced reverse engineer approach this? So I thought, I'm an experienced reverse engineer. What would I do if I sat down and dropped something into IDA and just saw thousands and thousands of move instructions and nothing else? So truthfully, I thought if I saw this, I'd go find something else to do. Because I reverse engineer because I think it's fun, but this doesn't look like fun to me. But more realistically, I think thinking about how we would reverse engineer such a thing brings up some interesting points. So if we had written that 99 bottles of beer on the wall program in C and compiled it, it would look something like this for our main routine, which just calls some of the lyrics. The first set of lyrics look like this. The second set of lyrics look like this. If you didn't use any functions, your 99 bottles of beer on the wall program would look like this in C. So really clear, concise, easy to understand and interpret control flow graph here. So if you ran this through a different obfuscation tool, you might wind up with something like this. A lot of obfuscation tools work by trying to add complexity, making things very, very complicated in order to make them difficult to reverse engineer. But if you have enough experience, even this isn't really all that bad. You can look at it enough and figure out which nodes matter, which nodes don't matter, which groups of nodes are performing more basic operations, and you can sort of reduce this into something a little bit easier to understand. So this problem is still kind of approachable like this. But in contrast, this is what the movfuscated 99 bottles of beer on the wall program looks like. It's it's a line. In fact, this is the ROT13 cipher that we saw earlier. This is the Towers of Hanoi. This is a Mandelbrot fractal. This is the Lost role-playing game. You might notice a pattern here. Pretty much everything looks the same. Not only do all the instructions look the same, but the control flow graphs are all identical. So also, when you try to actually look at this in IDA, IDA really doesn't like 100,000 move instructions in a single block. It crashes every single time you try to look at anything that you've obfuscated. So it's really kind of interesting that this works completely opposite of other obfuscation tools. Instead of adding complexity, it sort of removes all the complexity, and somehow removing complexity makes things really hard to reverse engineer because every single program ends up looking exactly the same. On top of that, there's really no way to reduce this. There's no way to simplify the problem because there's no dead code here. There's only code that sometimes works on fake data and sometimes works on real data. There's one thing you could do to try to approach this. A good reverse engineer would eventually see that you've got these same repeated blocks of move instructions, and they would be able to figure out what each block of move instructions is doing, and eventually reverse engineer the program back into the original brain yucky code and work with the brain yucky code instead of the 100,000 move instructions. It's actually pretty easy to thwart that approach. So I haven't actually done this yet, but it's not too hard to imagine. Most of the move instructions inside of these basic blocks are independent of one another. It's not hard to shuffle those things around in order to make no two blocks look alike. It's also easy to add junk instructions to these blocks to add diversity. A lot of the blocks are independent of each other, meaning you can interleave these different move blocks. You can even rearrange the different blocks, effectively making, if you wanted to, you could have this thing repermute the entire program every single time you compile, which is going to be especially effective in the move world where everything looks the same already. You'd compile it once and it would look like this, compile it again, it would look like this, again would look like this. So that's a lot to sift through, and that's really going to make it awfully hard to reconstruct the original brain yucky code from these programs. But even without this once in a while when I was making this thing, I'd make a mistake. I'd have a bug in my code. I'd actually have to dive into GDB and start trying to decipher what was going on. And even though I myself had just written these move instructions 15 seconds ago, I could not understand what was going on when I tried to watch the program run because every single instruction looks exactly the same. You just cannot keep track of what's going on when all you see is move instructions. So it was actually pretty effective, I found. It's not too hard to imagine some extensions to this idea. It's pretty easy to imagine substituting other instructions for moves. So for example, a pair of XORs, an add sub pair, an and or pair, a push pop pair. All of those can do basically the same thing as a move. So you could have an XORfuscator instead of a movfuscator if you so desired. I was sort of on a roll here and I was having a lot of fun with this. So I wondered where else I could take it. Earlier on I said that we were limiting ourselves to 1 byte data, which is a pretty big limitation. So I wondered how hard would it be to actually go beyond 1 byte data? How could I do 32-bit operations with movfuscated code? So I built a 32-bit arithmetic logic unit for doing 32-bit math here. The challenge with doing 32-bit math with move instructions is you can't just use lookup tables like we did with 8-bit math. You don't have enough memory for it. What you can do is cascade a whole bunch of 8-bit operations in sort of a ripple carry fashion in order to implement 32-bit logic. So these are the macros for 32-bit addition, expands out to this set of moves. That's actually not too bad. That's not a whole lot of moves for 32-bit addition. 32-bit subtraction is similar. The shifts get a little bit more complicated. This is the left shift as macros. This is the left shift as moves. It's the right shift as macros. This is that expanded to moves. Multiplication is where things start to get pretty hairy. So this is 32-bit multiplication as a series of NASM macros, which expands to this fairly monstrous set of move instructions. Division, though, and modulo, that's where it gets bad. This is 32-bit division and modulo as NASM macros. This is that expanded to move instructions. It's 7,000 move instructions to implement division and modulo, but it can be done because move is Turing complete. So our limitations with this approach really aren't in what we can do. We can do anything. I think it's pretty obvious our limitation is speed. The thing just runs way too slow to be useful. And really, if you think about how it works, the reason for our horrible speed is essentially that the way we have to implement jumps with only moves. Jumping switches between dummy data and real data. So if you can imagine jumping forward just a little bit, if I wanted to jump from here down to here, I switch data off, or I switch execution off here. I switch over to fake data. So all these moves execute but they operate on fake data. So it's just a bunch of wasted computation. But that's not a whole lot of wasted computation if we've just got a short jump forward. It's a short jump backwards that causes a bigger problem. If I want to jump from here to here, I have to turn execution off, and my entire program has to re-execute on dummy data before I can reach my short jump backward branch. And the problem with that is in Brain Yucky, short jumps backward happen an awful lot. So this is how, again, we set data to 0 in Brain Yucky. This is simply looping over the same memory cell over and over, decrementing it by 1 each time. So if you imagine if you had a cell set to 200, if you just wanted to set that cell to 0, your entire program has to re-execute 200 times in order to make that happen. So that's going to make things really, really slow and totally unusable. And just to highlight that fact, if we check on how our 99 bottles of beer program is doing, it's still churning away, and my laptop's not too happy about it. It's down to 60 bottles of beer. We'll get there, but this is pretty time-consuming for something that should have taken well under a second to run. So not the fastest thing in the world, not especially usable in its current state. But I'm sort of in this mentality, I've gone this far, I might as well keep going. So over the last few weeks, I built what I call movfuscator 2.0, which is actually a complete C compiler that will compile C code into only move instructions. So I did this by retargeting the LCC compiler. That's the little C compiler. I didn't really have any experience with retargeting compilers, didn't know what I was doing. GCC and LLVM looked really, really complicated. LCC looked almost doable, so that's why I picked LCC for this. It was an interesting little experiment. We needed a lot of registers just in order to do the memory transfers, in order to shuffle things around. So I had to reserve most of the registers for myself and left LCC with only ESI and EDI to work with, effectively turning x86 into a 2-register architecture. Had to make my own calling convention. None of the existing ones work very well for obfuscated code. Built an emulated stack through only move instructions. Integrated my 32-bit ALU. Changed the way we do dummy selectors. Instead of having duplicate copies of all our variables, we've now just got one big scratch space for the program to operate on when execution's off. I implemented all 102 intermediate language instructions LCC needed with only move instructions. And overall, this actually went way more smoothly than I ever could have imagined, especially given that I had no idea what I was doing. In fact, I think the only bad part about this whole thing was LCC uses GCC for a couple of pieces. Namely, LCC relies on GCC's assembler, and GCC likes things in AT&T syntax, which I just find abhorrent. So I had to write an awful lot of assembly looking something like that, which just felt gross and made me miserable by the end of the day. But other than dealing with AT&T syntax, this wasn't too bad. So I wanted to quickly demo the new version of the movfuscator, which works on C code. So I really just got this working pretty much last night. So I made this little nibbles program. It's a really ugly, short, simple version of the nibbles game in C. It uses ncurses for the video or for the graphics. Now we can use LCC to compile this thing. So I'm asking LCC to compile it using my new move x86 backend. So it'll build that, dump a bunch of debug information. Now we can check our program that it created. We can see our move-only version of nibbles. There's a couple, if you can happen to have really, really good eyes, you might notice that there's one non-move instruction in there every once in a while. It still does external function calls through a jump if equals instruction and a comparison instruction. So I've got a way to fix that. I don't have that implemented yet. But anytime you want to call into the standard C libraries, it's got to use those two instructions. But beyond that, it's really nothing but moves doing all of our work. So when we run this thing, we've got a version of nibbles now running with really only move instructions. And you'll notice it's actually fairly fast. This new version of the code runs blazingly fast, which I was fairly surprised about. But it's actually got a delay in here to make it a little bit more playable. But so the new version of the movfuscator, the C compiler, is actually produces fairly usable obfuscated code. So as far as I know, I think this is the first single instruction C compiler. I think it's the first single instruction compiler for any language that actually uses a real instruction, not a synthetic instruction, which is kind of cool. I'm still sort of in the mindset of where do I go with this now? So I've been trying to think of ideas for movfuscator 3.0. A friend of mine pointed me to this presentation showing that the x86 MMU is Turing complete. What that lets you do, it lets you do computation without any instructions. not with one instruction, with no instructions. And that's actually thanks to some guys that are here right now, I think, Julian and Sergey. So my goal for 2016 would be to have a no instruction C compiler, building off of what we've already got here, but we'll see how that goes. So wrapping everything up, I really don't know if this is a legitimate anti-RE solution or not. I haven't really spent a lot of time actually trying to reverse engineer this stuff. I really only made this because I thought it would be funny, but it turned out to be a really, really fun project. It's really interesting to see that Move can do anything we could possibly imagine. It's just a fun thing to work on all around. So if you're at all interested in this, I've got version 1 of the movfuscator. That's the Brain Yucky to Move compiler is on GitHub now. You can check that out to see how it works. I'll get the C compiler up as soon as I can. I want to get the code cleaned up because it's really ugly and embarrassing right now. And I still have to get permission from my employer to post that there as well. But I'd like to get that up as soon as possible. I was talking to a guy from Kaspersky the other day. He said, if you're going to do this, you really need to make a crack me for it. You can't give a presentation on an anti-reverse engineering technique and then not give people anything to actually reverse engineer. So the other night, I made the simplest possible crack me I could imagine. It's a 15-line C program. It's basically just a string compare, but I compiled it with the movfuscator, so it's just a bunch of move instructions now. So if anybody wants to try their hand at that, that's on GitHub as well. If anyone has ideas or feedback on this approach, I would absolutely love to discuss it. Hunt me down at the conference, or I just signed up for Twitter the other day so that I could actually talk to people here. So it's XOR EAX, EAX, EAX if you want to talk about any of this. So I've got a tiny bit of time left if there are any questions. And while we're doing that, we can see how our bottles of beer are doing. It's getting there. It tends to go a little bit faster as it gets further along, but I don't know if we'll quite make it to the end before the end of the presentation. So are there any questions people had? Yeah. The question is, what is the typical size of our binaries? Large is the answer. So there's about a megabyte of lookup tables for anything, no matter how simple the program. It's going to be at least a megabyte for your lookup tables. And then it's probably 100 to 1,000 times increase in the actual program size beyond that. So large. If size is a concern, this is not the obfuscation tool for you. Yeah. That's really depressing that it did not finish the bottles of beer. I don't know what the issue was there. But the question was, how did we skip over a call with the movfuscator? So for external calls, there's really no way. The only way to get, well, that's not true. A way to get to external calls, like in the standard C library, would be to use the call instruction. So that's basically what we have in the C compiler right now. You can do that through exception handling the same way that I caused it to jump back to the beginning at the end. So that'll be the next addition to the C compiler, is using move instructions only for calls. Yeah. I did think about targeting ARM. That seemed easier, so I didn't want to do that. All right, so I'll call it quits there. If you got any more questions, feel free to hunt me down sometime. I'd love to talk a little bit more about this. I'm really sad that the demo didn't quite get down to 0 bottles of beer on the wall, but I guess 98 is good enough for a day. So thanks, everyone.